So you want to scatter an object over a surface using geometry nodes, and what you typically do is to create the surface like a plane. Let's make it bigger, like 200 by 200 meters, and don't forget to apply the scale. I will also add some subdivisions here just to have some geometry to work on, and I will also create the object to be distributed, in my case a monkey head. Then you go to geometry node, you select your plane, create a new graph, and what you typically do is to add a distribute points on faces node, then an instance on points node, and finally, if you want to see the original plane, you also need a join join geometry node. Now let's connect the original geometry here. Here it is. For now, I don't see yet the object because I still have to connect it. So I'll take my monkey head, here it is, and connect this geometry output to the instance input. Oh, now I have way many two monkey heads. Let's reduce this density to 1. That's a bit better, but as you can see, my system is anyway lagging a bit because there are a lot of objects to be drawn. And the point is that in many cases, you don't really need all those objects because what you are seeing from your camera is only this part of the surface. So you really need to create objects in this viewable area, and you don't need all these other ones. You could need them only if they are seen in reflections or in shadows. But if it is not the case, it's enough to create objects only in this area within the rendered view. And this effect is called camera culling. How can you get it? Well, you can find some videos on YouTube about camera culling. There is a technique using dynamic paint, another one using the raycast node and an object to intercept those rays. And I was thinking there must be an easier way. So this is my proposal. What I'm going to do is to take my camera, drag it here, and also add a position node. Then I'm going to use some vector math, in particular vector subtraction. What does it mean? If you have two vectors, like a vector A and another vector B, if you compute A minus B, you are computing this vector, a vector going from B to A. And this is what I'm going to do. I'm going to make a subtraction between two vectors. First of all, let me cut this connection for now, so the system is not lagging anymore. For vector math, there is a specific node. It's called, of course, vector math. Here it is. Here we can do subtractions between vectors, and what I'm subtracting will be this position and the camera location. So what does it mean? Camera location is a single vector representing the position of the camera, while this position node is a field. So it represents the position of every point on the surface when it is computed by Blender, for example, for creating instances of objects. So what I'm doing here is to compute a vector which is going from the camera here to any point on the surface which is getting evaluated. So for example, if I'm computing this point P to check if I have to put a monkey head here, this vector will be a vector going from the camera toward P. And this is true for any point on the surface. Let me remove those annotations. Okay. So the next step is to use a vector rotation. And there is a node for that, vector rotate. I'm taking the Euler type of rotations, and I'm taking this vector and I will rotate it by the rotation of the camera inverted. What does this mean? Well, basically, if you check the camera rotation and you reset it, if you put the camera rotation to 0, what's happening? As you can see, when the rotation is to 0 in all the axes, the camera is facing downwards. So basically, if I am taking my vectors and rotating by the inverse of the camera rotation, I'm basically reverting this rotation, and I'm rotating everything as if it were in this situation. Look here, rotate. It's basically as if everything were placed like this. And this is very convenient because the camera optical axis is aligned with the Z axis, and if you look everything from the top, you can see that this camera now is a bit rotated. Here it is. If you look it from the top, the X and Y coordinates of the image plane now correspond with the X and Y coordinates of the world coordinate system. And this is very useful because it allows me to apply the fundamental camera pinhole model equations. What does it mean? It means that, let's open, this image. This is the pinhole camera model, and that's exactly what we have now. In the pinhole camera model, you have a camera here, and its axis, optical axis, is aligned with the Z axis, and then you have the image plane, which is the plane where the image is created. This is basically the camera sensor, and the axes of this image plane, X and Y, are aligned with the X and Y axis of the world. So if you have any point, let's call it P, not X, in the 3D space, and you want to find its coordinates in the image plane, this is new coordinates. Let's call them Y prime and X prime. What can you do? Well, let's look at this simplified view, 2D view from the left, from the side. And as you can see, if your point is here with coordinates Z and Y, you can find its new coordinate, Y prime, in the image plane just by using triangle similarities. And you will find that this Y prime is actually equal to F times Y divided by Z, where F is the focal length of the camera. So what I'm going to do now is to compute this value in Geometry Node. So first of all, I need the focal length of the camera. So I will add a value node. Then I select the camera. I go to the camera properties. Here it is, the focal length. Just right click on it and choose copy as new driver. Then go back to the geometry node, right click here and paste driver. Here it is. Now here we have the focal length of my camera. Then I have to divide it by Z, so I need to split this vector in its three components. So I need a separate XYZ node and then a math node to divide my focal length by XZ, sorry. And once I've computed it, I can multiply by y to get y prime, so the coordinate of this point in the image plane. So I need another math node, and in this case I choose multiply, and I multiply this value by y. And I can do the same for x, of course. So just duplicate this multiply node, and again I multiply the focal length divided by z, and I multiply it by x this time. So those are the nodes we have called. This is x prime, and this is y prime. Now we are almost done, because I just have to check if those coordinates fall within the image. In particular, within the image sensor. The image sensor is a rectangle with a coordinate system like this, x, y. This is the center with coordinates 0, 0. And I need to know the width and height of this image sensor. And I can find them again in the camera properties. For example, for the width, I just add another value node. I need to duplicate this. Let's select the camera, go to camera properties, open this section, camera. Now there is this sensor fit auto. Let's put it to horizontal, and here it is. Those are the two values we need, width and height. So, like we did before, right click, copy as new driver. This is the width of our image sensor, paste driver. This is width, let's call it W. And the same for the height. Here it is. Right click, copy as new driver, right click, paste the driver. This is the height, H. And let's take this camera and let's put this sensor fit back to auto. Okay. Oh, by the way, if you are concerned about measured units, this focal length is actually in millimeters, and here we are doing the computation in meters because x, y, and z are expressed in Blender units, which are generally meters. And so actually the result here is scaled up to a factor of 1000. But that's not a problem, because now we are comparing the value again with other measures that are again expressed in millimeters. These H and W are in millimeters, so we don't have to do any conversion. So let's check what we have to do. The width of this image sensor is W, so it's going from minus W over 2 to plus W over 2. And the same for the height, it's going from minus H over 2 to plus H over 2. So if I want to check if my point P is inside this camera sensor, I just have to check if its coordinate x prime in absolute value is less than w divided by 2. And of course, the same for the y. So let's do it. Here it is, our h and y must be divided by 2. So divide by 2 h and w. As we said, we need to compute the absolute value of x prime and y prime. But again, this is done with a math node. Absolute, here it is. We connect x and y here. And then we just have to check if our y prime is less than h divided by 2. So we need a compare node. I can use less than or equal. And is this y prime less than h divided by 2? The same, of course, for the x. Is my x less than or equal w divided by 2? And of course, I want both of those conditions to be true at the same time. One condition says that the point falls within this range. The other one says that the point falls within this range. And of course, if both are true, the point is here in the image plane. So we need a Boolean operator. So Boolean math. We need an AND operator. And let's connect this one and this one. And basically we are finished because the output of this node is a Boolean value, which is true if the point is visible from the camera and false if it is not visible from the camera. So I can just connect it as a selection input in my instance on points node here. This will say create the objects only if they are visible from the camera. Now we are not viewing anything because I disconnected this node before. So let's connect it back. Points goes to points, and here it is. As you can see, the objects are created only inside the cone of view of our camera. If I look from the camera, oh, everything is tilted here. Why? Well, it's okay. Let's look what happens if I move the camera. Yes, if I rotate the camera, objects are created only inside this area of view. If I zoom out or in, no problem. And let's see what happens if I change the camera focal length. This is important because you often want to change the focal length, and no problem. Also, if I change the focal length, everything still works perfectly. Okay. So there is only one small problem here. Let's look what the camera is looking at, and let's place it down here. Okay. My problem is that if I change the image resolution, this could happen. That the image area goes outside the zone where we have created our objects. The easiest way to fix this, first of all, is to check that this sensor fit option is set to auto, which is the default anyway. And in my opinion, the easiest way to solve the problem is to take those two parameters, H and W, which are the sensor size, and get rid of the smaller one. So let's take this H and delete it and use instead my W divided by 2. What are we doing here is to create some more points than needed usually. For example, if I have the standard resolution of HDTV resolution, as you can see, I'm creating some objects also in those areas which are not viewed by the camera. But the good point here is that if I change the resolution now, no matter how I change it, it will always fit this area where we created and scattered our objects. So as you can see, there is no way to escape from that. So basically that's it. The only problem I see in this configuration, but this is a common problem for everyone, is that if you want to use another camera, or maybe you just want to reuse this node setup in another project, the best solution would be to just append this graph in a new project without modifying the geometry node itself. But up to now, this is not feasible because yes, I have to select my camera here, but this is not a huge problem because this camera could also be published as a group input, and then you go here and select the camera, and that's okay. This W value, well, you should update it, but to be honest, I've never seen anyone changing the default values, so maybe you can just left this as a fixed value. 36 is okay. The only real problem is the focal length, because you do change very often the focal length of the camera. So if you apply this graph to a new camera, you have to modify it to redo this connection, so you have the focal length of your camera here. And I hope in the future this could be solved directly inside the geometry node. I hope that all those parameters of the camera, like focal length and so on, will be directly accessible, for example, from the object info node or from something similar. But up to now, I'm not aware of any way to do it. So this is the best solution I've found so far. I hope you enjoyed it, and bye.